Welcome everyone. My name is Dominik Nestler. I'm from Sentin, and greetings from rainy and cold Bochum, Germany. And yes, I know Martin saying that title, it sounds a bit like a legal disclaimer or something from a technical manual, but not exactly catchy. I will do better on the next one. But don't worry, I promise the rest of the presentation will be much more hands-on and a bit more practical. So let's dive into it. To provide you some context about the presentation and hopefully discussions we're going to have afterwards, I will briefly introduce Sentin and what we do, explain why we see such a strong need for tools that exactly do that, address inspection data quality, fraud detection, and other things. And then Stuart is going to join me. He is from Protect, an inspection service company based in the United States. And together we will walk you through some real world use cases that both at Protect and beyond are deployed to demonstrate how these technologies can actually be applied in the field and deliver value. So about Sentin, we offer AI and digital-driven solutions, and we do so by deploying our solutions, or as I like to call them, digital co-pilots, or as we see them in the field. And we want to redefine the inspection process by applying a virtual 4i principle to every inspection. A 4i principle, like you and I know from other lines of work where risk is involved, aviation, medicine, and we want to help our partners and clients with that to ensure that 100% of their inspection data is thoroughly reviewed, and that we're eliminating factors like the subjectivity or individual level of experience in the analysis of data and interpretation of it, and all that to deliver a high level of confidence and precision in every inspection. So to accomplish that, we combine deep industry knowledge by holding leadership roles in, for example, the German Society for Non-Destructive Testing, or also the German Institute for Standardization, for especially that AI in industrial inspections and non-destructive testing. And we combine that with the cutting edge technology and AI expertise that we have in-house that help us accommodate the unique requirements that we see across the industry. So all that means that we're basically able to build out our own co-pilots AI solutions, adapt them to fit different type of inspections, that will have the flexibility in deployment. I know that's always a big question around these topics. Is it all on cloud? Can be on cloud, can be on premise, hybrid solutions. So it's all tailored to meet the operational needs. And then we also cover the entire value chain when it comes to deploying and developing those co-pilots or AI solutions, starting from the model training, retraining of pre-existing models, data annotation, and also the integration into cloud or infrastructure, as well as building out custom workflows. With some of them we're going to see later on with Stuart and Protect. And with our digital co-pilots, we serve different clients from different sectors, such as manufacturing, mobility, infrastructure, and energy, including service providers, EPCs, and the asset owners themselves. Over the years, so we started about 6 years ago building out our technology and the underlying technology stack. And through that time, our technology has earned the trust of industry leaders, including being one of the first AI-enabled inspection solution services that is approved, for example, by Saudi Aramco. Now, that was hopefully enough about to get you to know us a little bit better and a better understanding of who we are and what we do here at Sentin. Because now I would like for you to see the world of the inspection through our eyes, and why we think that what we do, building out digital co-pilots and having that digital 4i principle, really matters to us. So now that we established that, I think it's easy to agree that inspections are critical for safety and reliability. Not much room for argue on here, but historically, and I have two examples I'm about to show, inspections can be responsible for introducing delays, inconsistency in results, and therefore action taken that might not actually need to be taken or is not taken because lack of results. And in some cases, even the inspection is the root cause for failures when, for example, issues have been missed. So like I said, I have two examples which I would like to highlight. One of them is a recently settled lawsuit from the US where two inspectors were charged with faking pipeline inspections. What they did here over the course of several years, they were faking reports, they were radaring, so duplicating images and submitting them for different measurement locations. And yeah, just did that over a stretch of years, never got caught until an incident happened and they found out what they did. And a similar issue was also brought to attention by the British Institute of Non-Destructive Testing back in 2024. They published an article where similar things happened in a production environment where also welds were duplicated or radaring was going on. And what they did here is after they shot the image, they used digital software to alter markers and identifiers so that it seems like they were shooting different type of welds and it was just hard to catch due to the large amount of data. And what that shows is that one of the weak links in the inspection lies in the fact that we're often solely relying on one set of eyes or only a human interpretation and the decision making that comes with it. And we can see in those two cases that sometimes data collection can be flawed, but even when that data collection is correct, misinterpretation of the data can happen, and that can have the same consequences and lead to underestimating a defect, maybe misclassifying corrosion, and just making incorrect assumptions or decisions on fitness for service, and just sometimes allowing unsafe equipment to keep operating. So this is basically why we believe inspections need a co-pilot. With today's available technologies, a human-only process or a process that only relies on one set of eyes, on one opinion, is no longer enough. So by leveraging AI-enabled and digital workflows, we can ensure compliance, protect integrity, and eliminate the subjectivity in those type of analysis, while also bringing speed, consistency, confidence to every analysis by a standardized process and standardized tool set. So now, after my hopefully strong case, why digital co-pilots are important for industrial inspections, let's turn the page and take a look at how we do that. How can a digital co-pilot be implemented in practice, and what impact can they have on operations? And to show that, we have partnered with Protect. And this partnership is not only for today's presentation, but we're working together with them to embed AI tools and digital tooling into their service offering, creating real values for their customers. And before we dive into the use cases, I'd like to introduce Stuart, who will be joining me for the rest of the presentation. So Stuart, give us a quick tour of Protect and what you guys do.
Thanks, Dominik. Thanks, guys. So my name's Stuart Beveridge. I'm the Senior Director here at Protect. And Dominik, if you skip on to the next slide. Just a brief introduction to give a little bit of context on the use cases of the technology we're looking at today. Protect, we aim to be different from our competitors, and we want to position ourselves as partners to our clients to create deeper service ties and ultimately an integration with our clients. We aim to be their first choice provider of field services and consulting services to help our clients operate safely, reduce their risk, and drive their operational excellence across all of their assets. at Protect, our internal charter positions us and is challenging us to become 100% technology-enabled company across all service lines and business units. And this is really where our partnership with Sentin here is enabling our growth in services and quality through the tools that we're going to look at today. So again, just a little bit of context. We are US and North America based, and we have 22 offices across the US. I am in one of 3 of our Houston offices. We have various service lines. We have 30 plus nested sites within our clients' facilities across 19 states. And I think we're probably even closer to 800 employees now than this slide. So some examples of the services that we offer and where we are looking to enable with technology and AI services across our reliability line through our mechanical integrity inspections, materials testing, NDT, conventional and advanced service lines, pipeline integrity, and then obviously some software integrations as well. And then across our risk and compliance side of our business, we have various service lines and business units where we focus on safety and environmental services, including permitting, process safety management, benzene waste management, and emissions control.
All right, thank you, Stuart. That was a quick introduction about Protect and to set the stage here. And now, like I said, we want to talk about some of the solutions that we provide and that Protect is embedding into their services and offerings. The first one that I would like, or we would like to show and discuss with you today is about weld integrity. Weld integrity is critical to the safety and reliability of industrial assets. Yet, as mentioned before, traditionally the X-ray inspections rely heavily on human interpretation, a process influenced by the individual experience, by the inspector, subjectivity, a level of focus, and on top of that, oftentimes pressure, which can lead to intentional shortcuts, as mentioned before, or just to rush through process to meet production quotas or something like that. So in this case, to ensure that this process is, let's say, done by the books, we together with Protect deploy one of our co-pilots to perform a standardized and data-driven inspection process. So each X-ray image of a weld is automatically analyzed against standards and procedures like the API 1104, ANASME Section 5, or even company-specific procedures that are built on those international standards and have some sort of configuration to it can be built out from that tooling. And now the system takes in the image and produces a report that is gives a quality scoring and has detailed explanations for further assessments, as you can see here on the slides as well. And maybe Stuart, tell us how you utilize that tool and what are some of the early insights that you guys gathered from using that?
Yeah, absolutely. So there's this tool here specifically. There's 2 main cases that we're utilizing this. We're building this into our internal workflows. So if Protect, we go and provide weld X-ray services, then we are analyzing those images and the data that we gather through this tool as an internal QA/QC process. And if we are gathering that information through digital X-ray radiography here, we're essentially almost able to do that within real time as that image is taken and analyzed. That image is passed through our digital workflows and returns very quickly to our field teams a thumbs up, thumbs down. So this meets requirements that we're looking for, whether it be API 1104 or B31.3 standards or specific company standards. Another way that we are applying this is to work with our clients as that trusted third-party quality team. So what the report screenshot is actually on the screen here is we asked one of our clients based in Texas to provide us some files which they have received from various service providers, has been QA'd internally by those service providers, has been handed over to the client. The client has reviewed and QA'd and accepted them, and for us to re-review them using this technology to see and essentially audit that process. And what we found was there were absolutely cases where those image requirements were not met, even though we'd had 2 levels of that human QA, both internally within the service provider, but then also on the client side. So again, it just re-emphasizes the point that Dominik was making, that people make mistakes, people have certain biases, that even with human eyes and things that they prefer or dislike, there are things that do not meet code requirements, such as the images on the screen here, that we are very quickly and easily able to report on and get that in front of the right people to make decisions.
Thank you, Stuart, for summing that up. And that directly leads me to the second co-pilot that you guys have in place, and we also can or going to go elaborate a little bit on how that workflow that you already described on the quality tool can look like, because that also is a big part of the co-pilots or AI tools in general. It's not only about having a great tool that delivers a certain outcome. I think that just as important is to embed it in the workflows, in the processes, and be able to, in some cases, build processes around that to deliver meaningful results also in a fast manner. And for that, exactly, I think that is a great use case. So again, we're looking at X-ray images here, but we're going to look at a different task at hand, which is to analyze the pipe wall, checking for thickness loss and identifying points of interest for maybe corrosion mapping and so on and so forth. And also embedded in here is a way of smart calibration and measurement, so that we find a comparator on the image, calibrate the system, so that basically the entire analysis of that profile shot can be done automatically. And again, gives you a clear visualization of the tool by sort of a heat map along the profile, and gives you a better indication of the overall status of that. And basically what's happening in the background, we have something that detects the pipe wall, an AI-based algorithm. And based on that piece of information, we can apply a multitude of measurement points along that profile and generate hundreds, if not thousands, readings along that profile, and then can come up with that heat map if you want, and also can highlight areas of interest, being what is my minimum reading here, what other types of things can I see here. So this is the overall concept of that tool. And again, maybe Stuart will skip to the next slide, and you can chime in on what you guys found and how that is delivering value to you and your clients by using it.
Yep, absolutely. So again, we asked one of our clients here in the US to again provide us some profile radiography data, again, which had been provided by a service provider and accepted by the client to review that data set again and look and see how accurate were the humans. Did they find the lowest point within that pipe, or were there a potentially thinner location, which could be influencing repair replacement decisions, or be able to catch those thinner locations before that failure could potentially occur. And what we found was pretty shocking or startling, that in almost 1 in 2, so almost 50%, 45% of the data sets, we found there was a thinner location than what the human eye had picked out and determined within that image. Some of those differences were small. Around 60% of them were less than half a millimeter, or 20 mils for any Americans joining us today. But over a third of them were more than a millimeter of a difference between what the human had found with their eye and measured with their eye and calibrated against, and was handed over and accepted and was long-term data storage by that client, and what that true minimum thickness was within that radiograph X-ray. So yeah, really significant findings there from that case study from that client. And we're also working a second project now to look to re-review across a wider set of data for that client as well. One of the ways that we have implemented this within our technician and inspector workflow is that we have set up some automated workflows which look to take some asset information from that primary inspection data management system, whether it be a PCMS, an APM, or our internal version of Shield, where we're tracking and managing that integrity program. What our technicians there can do is they can download their information before they go into the facility, out to the field, wherever they are going to be doing the inspection. They can download it digitally onto their phones or tablets. From there, they will perform the inspection. At that point, they can load that profile radiography into the Sentin software, which can then connect wirelessly and digitally to their handheld device. From there, the analysis is performed. The data is extracted, analyzed, and sent back to their handheld device, where they can complete reporting, take images, annotate, complete that inspection, do any checklist style inspection, automate reporting, including the profile images and the profile measurements, submit that information, generate that PDF report automatically, and then submit that into whether that long-term storage system is our internal Shield system or a third-party system, and have that review QA approval process there. So really digitizing that full workflow, not just the analysis of that profile, but the full technician workflow, which means that as they walk away from that facility, that asset, their data is submitted, waiting on QA QC.
Yeah, thank you, Stuart. I guess it's not going to be a surprise that I asked Stuart to show exactly that workflow, because that is one of the questions that I or we get asked the most is when we talk about the co-pilots on themselves, is how do I get the data to the co-pilot? How does the analysis work? How do you get results? So I really like what you guys at ProTech did here together with our team to incorporate that into your workflows, because that really shows the true benefit if you build a process around the tool, that you have a real like seamless, no paper trails, and fast turnaround also for getting the inspection insights to then perform the actual repair work or use for further analysis. There are no system breaks in terms of a printed out report, typing in values. Again, that is introducing another or more room for error, basically, by typos and so on and so forth. So I think that's a really cool thing that you guys build out there, to have that in a full digital workflow, really harvesting all the benefits that the technologies bring, and how you can interact, what they can interact with each other to bring that out.
Yep, absolutely.
And then I know you got one more to present that is outside the world of X-ray. Yes.
So this final use case or case study that we're going to talk through today is focused around, in the US we call it LDAR, leak detection and repair. Essentially, it's emissions monitoring, various valves, flanges, etc. And what we're looking at here is we're not so much looking at the analysis of the data or the ppm of VOCs. What we're looking at here is more of inspect the inspection. So are we confident, and do we have trust in the values that were generated and the inspection work that was complete, rather than looking at the analysis or the values created, but can I trust the values that have been submitted? So again, two example case studies here. The top chart, what the technician was asked to do was walk from valve to valve, flange to flange, and measure VOC readings with a handheld device for at least 60 seconds before then moving on to the next location. They would have their route planned for that day, and they may have 50 locations, they may have 200 locations within that day that they have to walk around the refinery or the chemical facility or wherever that asset is. The top chart we see here, we're looking at the personnel's movement time and their actions rather than the actual readings of that ppm of VOC. So what we would expect to see is valves and flanges are different distances apart. We would expect to see variation within those green dots, which we do. Sometimes it takes 20 seconds, sometimes it takes 2 minutes to walk between those readings. So that is a good trend. We also ask them per procedure to take a reading for at least 60 seconds before moving on to the next location. And all of those blue dots were at least 60 seconds or above. So without even looking at those ppm measurements, the values that technician recorded, I have general trust that this person followed procedure and I can accept and trust their readings. The chart at the bottom, the person was asked to do the same job. So rather than taking a variation of time to walk between valves and flanges, they were averaging around 2 or 3 seconds. They were also asked to take those measurements for at least 60 seconds. And out of those 200 readings on the screen, not one of them was taken for over 60 seconds. So what this does here is, from this leak detection testing here, is without even looking at this technician's results, I have no trust that they did not follow the procedure, they did not follow the requirements. So their results, their data, we cannot rely on for valid reasons and reporting within the US to the EPA here. So this allows us to really screen and monitor the technicians and the inspectors and add plausibility and trust to the results on top of what the actual inspection outcomes are. Then this is an additional layer of audit on top of that here.
Thank you, Stuart, for covering the leak detection and repair analysis as well. Maybe from my side to add just a few little notes on the technical layer of it. So what's happening in the background here, what we're looking here is that at the chart on top, and establish sort of patterns that we established with these subject matter experts from ProTech to be normal behavior or something that we're expecting to see in the data set. And then what we built based on that is basically sort of a pattern recognition, well-established concept in the realm of machine learning and artificial intelligence, which we then can apply to larger data sets. So of all the collected data incoming to analyze trends and also catch those outliers that we see on the bottom chart to then early on, again, give out an alert review to the quality control crew to check the actual readings and see if there's anything striking as well, so that they have a better overview of establishing a real overview of the quality of the data instead on relying on just sample sizes, for example. So again, thank you, Stuart, for chiming in on that presentation and presenting some of the digital co-pilots that you have deployed throughout your organization and some of the different use cases. Now I would like to do a quick callback to why I showed you those two examples, because some of you may be like, all right, Dominik, cool that you showed those two, but is there anything we can do about exactly that? So radaring, duplicating X-ray images and submitting them for different wells. And yes, good thing is there is also something that we're working on, trying to find that needle in the haystack. So we have a tool that we tested in a first project that's still in its early stages, but a good track here, where we start to take in images, X-ray images of wells. And basically what the tooling is doing, it's comparing all X-ray images with another. And what we can see is it's a big task that you probably couldn't ask an operator to do, because only with a couple of hundred images, you're already getting combinations of 5,000 plus. So hard to cover without the appropriate tooling. And in here, there should be a little video that's showing how it works. So we see on the left-hand side the images that have been analyzed, and then those are the two that have been flagged as potential duplicates. And as we can see here, what the tool basically does, it's looking at what is called, or what we call, the fingerprint of the weld. So distinctive features that we find in a weld. And I think if I let it go for just a little bit more, yes, it's highlighted in this area that we see that those two areas are pretty much exact the same thing, but so it's the same weld, basically shot twice, but submitted for differing measurement points. And like I said, we did that in a first test project where someone handed over their data and wanted to have a quick review at what we found. And a small part of that data was rather shocking, that almost 70% of those X-rays were actual radar shots. And so this tool basically helps sorting those images according to their likeliness to be a duplicate or be radar welds, and give the, again, QA, QC in this instance, even the chance of catching those early on and making that visible to the operator in a larger data set. And then this can also be run on, let's say, historic data. So if you have a large data set and getting new data, doesn't have to be, all of one single project, can also be against the historic database that you have built. Of course, that means that we need to have those X-ray files at hand in a digital format. And yep, that would be the last piece of technology or Copilot that I wanted to show you here today to address that issue of radar welds, which is a topic not often discussed, but the law case, as well as that study from the British Institute and that project that we had here, show that it can be a potential issue in terms of safety and reliability, especially for large asset owners. And with that, thank you very much for being with us here today, staying through that presentation. Stuart, once again, thank you for joining me here and presenting how you deploy those tools, and looking forward to your questions from the chat. And also, if you have any more questions afterwards, feel free to reach out either to Stuart or to myself. Thank you.
Thank you very much, Dominik, and thank you, Stuart, as well for that. A very interesting presentation is we normally think of AI and machine learning in terms of automated defect detection, but it's good to see that it's been used here in terms of following the whole process through. There's quite a few questions coming in the chat. A question from Brendan Watts. This relates to where you were finding thinner areas than were humanly detectable. Do you have thinnest point assessment error as percentage of nominal thickness rather than as an absolute thickness error?
Absolutely doable in terms of how we display the results. Yes, could be adapted to display that. Could also display multiple readings. Doesn't necessarily just have to be the thinnest or lowest value. So that is one of the parts that I mentioned early on in the presentation, where we're able to customize a lot of that, especially when it comes to what is the most valuable outcome to your operations.
Another question from Michael Sim. How do you see AI technology improving rope access works?
Good question. So other than whatever craft is being performed on rope access, where we have seen it used elsewhere, potentially not internally yet within ProTech, is a lot of the kind of the planning of it. So we have started to look at with one of the EPC contractors over here within the US of how can we better plan the service to be provided. So not so much the inspection result side of it, that would depend on whatever craft we're performing on ropes, but also on the planning and execution side of it, various simulations and looking at different pre-planning options, I guess.
I had a question relating to the following the process through using the AI Copilot. It looks a very effective way of verifying that that the actual inspection process has been followed through. Does any of that information go back to the inspector themselves in terms of them being able to sort of use the output to verify that if there's anything they might have missed during their sort of calibration and setup process?
Yeah, absolutely. So as the data is being gathered by the technician, it is also being processed at the same time. So as they gather data, whether it be the profile radiography, for example, when they take that and analyze it, as part of that analysis, the AI Copilot is built into that analysis workflow. So it's also the technician operating that part of it, reviewing that part of it, getting that feedback, whether it be profile radiography or in the weld image quality that we looked at first. It will give them that feedback that, yes, this meets requirements, or no, it does not. And if we couple that with digital radiography at the same time, we can have it almost real time, that as they are still set up and taking those digital radiographs, they can make any adjustments and reshoots that they need to make there and then as well.
A couple of questions in the chat. One from Muriel Bockchard. I think it's probably answered, Muriel, in terms of the later elements in talk. I'm not sure how AI is utilized. Is it defect detection or for other processes? I think you probably answered that during the talk. How was the AI machine learning process for weld inspection verified? How many data sets did you need to verify the AI model, and was it using both real and simulated data?
So for those that we have seen here today, we've used real data set, gathered over the years, gathered on client projects, and also verified on that data within the projects. And so hard to say what the total number of images have been going through the training and through the validation process, but part of each co-pilot going into action basically is a validation process with the client. And I've seen in the chat some questions about ground truth. Ground truth meaning that single source of truth to be in it. If there's the case that the system and an operator disagree on something, how do we establish who's right, who's wrong? So that's also something that part of that, let's say, ramp up of the tool or building it in is just part of that with the client that are at the end utilizing the technology based on their data, their procedures. And also the way that we use the technology is that we rather want to be on the safe side of things. So if we would go back to the report on the quality, there were 3 sections that were basically a bad or reshoot, a review, and a good. And we have that review section in there, for example, to cover all of those things that are some sort of either in a gray area or where some of the confidence level of the algorithms in the background are not at a set or at a certain, let's say, threshold. Instead of marking them as good or bad, we rather have them for review so that an operator can over them, so that our priority is that we do not want to miss anything. So we might have a few more false calls, but that's all to make sure that we have that extra level of reliability that we want to gain through the co-pilots.
Yeah, no, that seems a very sensible approach. You're really indicating where there might be something to the inspector that they make the ultimate decision. This question here from Sura Mulaluri. In your case study of X-ray image, the software must be looking at pixel level information for analysis. How effective is it in terms of probability of missing out, producing reliable results in the case of if the image is not proper? So if there's issues with the quality of the image, how's that taken account of?
So there's different parts to it. Of course, we're also looking at, let's say, pixel level, and are looking at gray values, gray value distribution to see if what would be density in conventional X-ray is met in the digital world. So we do have that type of analysis based on the gray values, but most of the analysis basically is done on based on computer vision, meaning that basically we trained the co-pilot to do the same thing that we would do assessing that image. So looking for IQIs, looking for lab markers, and that is done using, like I said, AI or computer vision would be the term. So applying machine learning on that to identify those assets. And then we have a whole set of rule-based algorithms that come from the codes and sections of it, and then say if the IQI is placed XYZ, that means it's good or it's not good. So it's a bunch of combination of different moving parts that are tied in together and all under that umbrella of the codes and regulations.
Great. Okay, thanks. Simple question. There was an estimate given as the percentage error in terms of the weld inspection, and the question was how about as percentage of nominal wall thickness? I think that was where there was some the actual manual interpretation was shown to be an error by 0.737 millimeters, I think.
That's right. I would need to check with the data sets to compare that against their nominal thickness. I don't have that information right in front of me right now.
Okay, an interesting comment from Patricia Lidicott about where the AI showed thinner points beyond the capabilities of the human inspections. What the comment is, this might be a challenge on aging assets, i.e. finding justifying defects that were always there and not found previously, which then may become an issue. So previously okay areas will then need to be tracked because a defect has appeared. This would probably be a regulator requirement. So I think it's a comment. Do you have any
a good one.
thoughts on it? It's a good one, yes.
Yeah.
It's an interesting one. I mean,
Definitely.
I think my view would be that the better the condition information is to the reality, then I guess that's, and if it does throw up additional defects, then you know more about the condition. So
yeah,
anyway,
absolutely. So we're hoping to avoid the ignorance is bliss. If we don't know about it, we don't need to do anything about it. We're hoping to take the stance that the more you know, the more you can manage and proactively manage, hopefully.
Okay, there's a question here from our third author today, which needs a knowledge of AI and machine learning, I think, to understand. Can you share more detailed accuracy stats like the F1 score, etc.?
Happy to discuss all of that afterwards. So just shoot a message. Let's jump on a call and get into the details.
Okay, great. Yes, Jonathan, if you just put your email in the chat, then we can pass that on to. I've got it anyway. We can pass it on to Dominik.
Sure.
Okay. Question from Rafael Martinez. What is the meaning of LDAR, which you responded to, leak detection and repair?
Yes.
Right.
Okay. Question from Peter Loftus from RCND. What advice do you have about gaining approval from regulators and insurers for the use of technology to aid decision making?
So the way that we have framed that as the co-pilot as an assisted service, I think that is the way to go as of now, that these systems are not solely making the decision by themselves. They just help to make better informed decisions, and some of them in a faster fashion. Like I said in the beginning, we're part of different bodies that are working on regulation for AI, especially in industrial inspections and NDT. And I guess this is something that if we get any sort of guidance or regulations on how to validate those type of tools, then this will become easier to get that approval from regulators and insurers to use. On the other hand, we actually have for other use cases, insurance companies that are turning to us and be like, hey, we have a huge bunch of, for example, drone footage to analyze of our assets. Takes us tons of time. Can we give it to you and you do a first set of analysis? And whenever you find something, we do the more deep dive work of it to carve out better insurance policies, get kickbacks from their reinsurance companies. So there's a certain level of trust, but like I said, we like to frame them as co-pilot that assist you making better decisions, not take bad decisions away from you.
Great. There's another interesting question that really follows on from that. could this product compare two different DRT shots to the same pipe, which were done in a different time period, and find differences in corrosion rate, etc.?
Yeah, absolutely. So rather than currently where we may take a profile of an elbow, for example, and we measure the thinnest point, and then in 5 or 10 years' time, we come back and we reshoot, and the thinnest point is at a different location, and we're comparing minimum measure thickness to minimum measure thickness, and may not be at the exact same location, because this profile tool is generating hundreds or thousands of data points. We can compare them apples to apples, so we're able to get a much better profile of that corrosion behavior over that 5 years, 10 years, or whatever that time frame is.
Okay, yeah, I was interested when you're talking about the drones, as people use drones a lot for doing sort of LiDAR or 3D photogrammetry and looking for corrosion, the surface condition of things like flares, equipment, etc., or corrosion on the platform. And I guess that potentially there you could maybe compare the last LiDAR inspection with the latest data to see if any corrosion changed. Great. Well, I think we've come to the end of the time for discussion. It's very interesting to see the AI machine learning used in this way of validating the process. I thought also within the digitalization forums, we talk about the end-to-end data flow of digitalization through from the NDE acquisition through to the use by integrity engineers. And it seems from what you were showing about the AI following the process, it seems that that's something that's not only been done, you're actually able to validate that that's been done. So
absolutely.
Thank you very much for your presentation, and
thank you.
Look forward to the remaining ones. Thanks, Stuart. Thanks, Dominik.
Thank you.
Thanks for having us.
That's right.